Okay, hello guys. We're gonna finish this ratio test, and then we're gonna do uh, another one that's called root test. Or sometimes it's useful to have that one too. They're similar, uh, and and then we're gonna start understanding how this is important to define new functions. Okay, so we're gonna start talking about power series. So let me go here and give you more example of this ratio. I'm gonna share my screen now. This is ratio test. So let me give you more examples. So let's go and solve this one. So example, we need to decide if it's convergent or divergent. So is the sum of n to the n over n factorial n equals 1 to infinity convergent or divergent. So as I said before, when you see this kind of weird stuff, like it looks difficult, right? Like n to the n over n factorial, the sum of that looks kind of difficult to use any other test. So it's just, you just can't tell that it has to be ratio test, or the other one we're gonna do is root test. So remember, to use the ratio test, I need to find the limit of an plus 1 over an, n goes to infinity. And if this limit is L, and if it's less than 1, the series is absolutely convergent. Okay. So so that's what we're gonna do. So we're gonna do. So remember, this guy here is this guy here is A to n. Okay. Okay. So let me give you 3 minutes. So you write. So you write what is an plus 1. So you write what is an plus 1. So let's put it here. You're gonna put right here what is n plus 1, and then here you're gonna do the quotient, an plus 1 divided by an, and take that limit. Okay, but make a serious effort. Okay, so you can learn to find these limits, because you have to, in order to understand, you have to try it. Maybe you did something wrong. Maybe you can ask me if you can do this or not, and then you learn to do it. Okay, because this is how to you. Is one of the most important ones. Okay, ratio test is really what you need for the next 3 sections. Okay, really important. That's how you understand the real physical problems. Okay. Okay, so I'll let you I'll let you 4 minutes to try to find this limit. Okay, so what is n plus 1? So please somebody tell me. N plus 1 is?
Is it n plus 1 to the power of n plus 1
Yes. And what else?
over n factorial plus 1?
N plus 1 factorial.
Oh, okay.
N plus 1 factorial. Okay. So then we plug in that over here. So that's n plus 1. So that we'll do n plus 1 to the n divided by n plus 1 factorial. And then an is n to the n over n factorial. So we do the thing again, the eating rule. So when you multiply, you get a limit n goes to infinity of, so we'll get n factorial times n plus 1 to the n divided n plus 1 factorial times n to the n. Okay. So now, so what is n factorial? N factorial is, by definition, n times n minus 1 times n minus 2, and so on until 1. Divided by n plus 1 factorial. So that one is n plus 1 times n minus 1, and so on.
Sir, isn't it n plus 1 to the n plus 1?
What? Factorial?
Yeah.
No. No, start
Oh,
decreasing.
no. On the first limit, the one that matches to an plus 1 on top. N plus 1 to the n plus 1.
I don't know. I don't know what you mean. So I multiply. So do you mean the Euler law or what?
Yeah, but the one on top, isn't
So
it n plus 1 to the n plus 1?
It's n factorial times n plus 1 to the n. And then n plus 1, it doesn't matter the multiplication because it's multiplication. You can put it in.
Oh, okay.
Because it's multiplication. Okay. So I just put it so you can see n factorial divided by n factorial and powers with powers. But it's multiplication, so it doesn't matter. So then we go n cancel with n minus 1 cancel with this one, and so on. Okay. So all that I have is, what is left? After simplification, what do I have? Of n factorial divided by n plus 1 factorial is just
N plus 1.
on the bottom, right?
1 over n plus 1.
Thank you. Yes. 1 over n plus 1. Because the n cancel. This n cancel with this n. So I just had 1 over n plus 1. So what I have is limit of n goes to infinity. And then 1 over n plus 1 times n plus 1. And let me put it together. N, the whole thing to the n. And like this. Actually, in we our simplification is n plus 1. Oh, okay. Sorry, I have here a mistake. So I over here, so you see I need to put n plus 1 over here, right? This is n plus 1, right? So I cannot meet that n plus 1. I didn't double check, sorry. So this is n plus 1 is n plus 1 to the n plus 1. So I was missing that n plus 1. Okay. So with that, so I have to be careful here because I better don't go that fast. So I have n to the n plus 1 times n plus 1. So I can do n plus 1 times n plus 1 to the n. And this is n to the n. Do you guys see it? So remember, this is fundamental. A to the n times a to the m is a to the n plus m. That's what I'm using here. But just with 1. N plus 1 to the n plus 1 is just n plus 1 to the times n plus 1 to the n. Because this is a. This guy is a. And this guy is a. So a times a to the n is a to the n plus 1. Okay? So that's where I have to be careful. So then I cancel this guy with this guy. Because both are n plus 1s. So now I have the following to see who remembers this limit. Limit n goes to infinity, n plus 1 to the n divided by n to the n is the limit of n goes to infinity the whole thing n plus 1 divided by n to the n. So what is that? Somebody remember that limit? Or you can put a limit n goes to infinity. 1 plus 1 over n to the n. So that's probably the first limit you do in calculus 1, and you do it using calculator. Like, well, probably my second example when I do calculus. Of what is the limit? Somebody remember? Nobody remember? So this limit is e to the 1. So that's kind of, that means the normal exponential number, 2.71, etc. So this limit is less than 1 or bigger than 1?
Bigger than 1.
Bigger than 1. So this series is convergent or divergent?
Divergent.
Divergent. So this series is divergent by the ratio test. Okay. Okay. So let's make another one. So so let's see if this test is, let's see that this test is almighty or not. Let's make it one that we know. We can do, yeah, let's do just this one. Example. Sum of 1 over n equals 1 to infinity, is divergent or convergent? So we know the answer, right? So what is this series? Is this series convergent or divergent?
Divergent.
Divergent. So let's try to apply the ratio test. Let's apply ratio test. So we have a to the n equals 1 over n, right? So what is an plus 1? If an is 1 over n, what is an plus 1?
1 over n plus 1.
Yes. And then we find the limit. So the limit, the n goes to infinity of an plus 1 divided by an. This is limit n goes to infinity, 1 over n plus 1 over 1n. And then we do, so let me give you 1 minute. So find me that limit, okay? So tell me what you got. So what do you get? When you multiply this, what do you get? limit n goes to infinity. So what is on the top?
N over n plus 1.
N over n plus 1. So what is this limit?
Divergent.
But what is the limit? Oh, the limit is divergent? No, the limit is not divergent. So remember our trick, right? How can I find this limit? I
By
did.
splitting. Oh.
Sorry, what?
You split the top and the bottom, you find the limit of both. Or no?
No, because the top is gonna give me infinity and the bottom is gonna give me infinity. So I wouldn't get any information. I mean, sometimes that work, but in this one doesn't work because both will be infinity. So what do? We divide by
N plus 1?
N.
Oh.
n. So we divide by n everything. So we divide by n over here, divide by n, divide by n. Then we get limit. Sorry, limit n goes to infinity. 1 over 1 plus 1 over n. So what is this limit?
Is it 0?
No.
1.
1. Now you can split limits because the limit of the top exists. So you couldn't split limits on the top and bottom because both limits didn't exist. Here you were having infinity over infinity. But now you can split limits. You can do, since you guys wanted to do, so let's do it. So you go limit of the top, 1 n goes to infinity, over the limit of the bottom, 1 plus 1 over n. And so the limit of the top is 1, right? Because it's a constant. And the limit of the bottom is also 1 because this guy goes to 0. So I get 1 over 1. So this is 1. So what the ratio test said when I get the limit equals 1? So
That would be divergent.
no. So the ratio test does not decide. Ratio test cannot decide. Okay. So the ratio test is not almighty. Okay. It does not. So if get you 1, then you have to find something else. So that's why we do this one. We did this one with integral tests, right? Or similar is a P series with P equals 1, so it's divergent. Okay. Okay, the last one. Then we move on. So take this one, this example series, okay? This is my last one of this ratio test. So if I could make a quiz right now on this, but since we are face to face, it's too difficult. So is this series convergent? Sum of minus 10 to the n over n factorial, n equals 0 to infinity, convergent or divergent? So go ahead, let me give you 5 minutes. So do your best to get this right because this is the kind of example you're going to have in the homework and in the exam. Okay, let's solve it. So what is an? An is minus 10 to the n, where n factorial, right? So an plus 1 is minus 10 to the n plus 1 divided by n plus 1 factorial. So now I can do the limit. Limit of n goes to infinity, n plus 1 divided by n. Actually, absolute value, right? I didn't put actual value in the past, but because they were natural numbers, but they're supposed to be actual value. But since they're positive, I didn't put it. But here, don't forget it because that's gonna save us. Okay, because you can write this like because we have the let me put it like this: limit n goes to infinity. So you an plus 1. So we could put it like this: minus 1 to the n plus 1 times 10 to the n plus 1 divided by n plus 1 factorial. And the whole thing divided by an. And an is, let's put it like this: minus 1 to the n, 10 to the n over n factorial. And now we took this is with absolute value. So that's great because the minus 1 is going to cancel both places, on the top and the bottom. And then I can do my eating law, my yield law. So I get limit n goes to infinity, and then it will be the minus 1 disappears, and I get n factorial times 10 to the n plus 1. And then the other will be n plus 1 factorial over 10 to the n. Oh, yeah, 10 to the n. Is that right? Somebody got that? Let me check. N factorial 10 to the n plus 1 and 10 to the n plus 1 factorial. Okay, so now we cancel. So try to not cancel, but try to simplify stuff. So between 10 to the n plus 1 and 10 to the n, what is that? You try to simplify these two, what do you get? What do we get? So you have 10 to the n plus 1 over 10 to the n. You get 10 to the n times 10 divided by 10 to the n. These two cancel, right? So out of these two tens, I just got one 10 on the top. So I'll get limit n goes to infinity. I'll put 10. And what is n factorial? N factorial is, and do the other one, guys. What is n factorial simplified with n plus 1 factorial?
1 over n plus 1.
Yeah, correct. We already did that one, so I'm not going to do it again. So we get n plus 1. So we get, what is this limit? What is this limit? When n goes to infinity, this limit is, so you can take 10 out. Limit n goes to infinity, 1 over n plus 1. So what do you get? You guys know this from calculus 1. You know I had to write a letter to your professor. What is the limit? When n goes to infinity. So you just plug in numbers, right? So 1/6, 1/7, 1/8, 1/9, 1/10, 1/1,000. So when n is increasing, what is 1/n plus 1 going?
To 1.
No.
To 0.
0.
0. So let's put it here. N and 1/n plus 1. I don't think you guys are thinking straight. So if n is 0, I get, what do I get? In 1/n plus 1.
1.
1.
1. If n is 1, what do I get on the right?
1/2.
1/2. Now let's make it big. If n is 10, what do I get on the right?
1/9.
11, because 10 plus.
11.
And then if it's 1,000, what do I get? 1/?
1001.
1001.
Mm-hmm. So you see it's going to 0, right? Oh. So when n is going to infinity, 1/n is going to 0. So this guy is going to 0. So 10 times 0 is 0. This is less than 1? Yes. So this is convergent. Okay. So let's take a little break of these limits. So let me show you what is this good for before going to ratio test, root test. So you guys see what are we doing all this thing and why do we care at all? Okay. Well, it turns out that between tomorrow and next week, we're gonna probably see the most important theorem from calculus. And this is forever, even for when you are an engineer. It's about approximations. So all that we have been doing is exact. Okay, you find the integral exact. Except when we do approximations like Simpson rule, trapezoid rule. But the real idea of this, the real power of this, is power series. So let me call here power series. So what is a power series? So a power series, I'm gonna do it like not a definition, etc. for now. It's just formal, okay? So a power series is basically an infinite polynomial. Okay? So a power series looks like this. So let's say sum of an x to the n equals 1 to infinity. So basically, it's an infinite polynomial. So you spend a lot of time in college algebra and in high school working these guys. So the first one will be, well, we can start at n equals 0. So we'll get a0 x0 plus a1 x to the 1 plus x2 x to the 2. And then you keep going until infinity. Okay? So when you get x0 to the 0 is just 1. So this is a0 plus a1 x plus a2 x2 plus a3 x3 and so on. So what I promised before was that you will be able to define the functions we work with, like exponential function, logarithm function, all those functions that are continuous we can express it like a power series. Okay. So let me give you the first one. So this is exponential is given by this formula. I mean, right now you have no idea where it is coming from, but you know, this is a motivation. I'm trying to motivate why this is important. Why we care about series and why we're gonna, what we can do with this. So this is gonna be the following, that it's gonna be x to the n over n factorial. That's why the root test is gonna be important here. This is from n equals 0 to infinity. So the exponential function can be written, when you plug in 0, you get x to the 0 over 0 factorial. So by definition, 0 factorial is 1, okay? 0 factorial is 1 by definition. So everything, well, okay, let me put. The 0 factorial is not 0. Okay, you have to be careful in your exam, okay? Otherwise, you're gonna affect your grade. And then this will be plus, you plug in 1, so you'll get x over 1, right? Then at 2, you get x squared over 2 factorial. What is 2 factorial? What is 2 factorial?
2.
2, because it's 2 times 1, right? Plus x3 over 3 factorial. What is 3 factorial?
6.
6. Oh, okay. Camila needs to say goodbye. Yeah. Bye, Camila. So,
Yes, sir.
okay. And then, and so on, okay? So this is your power series for exponential. So how can I convince you of that? Well, let's start graphing it, okay? But this is a theorem. This is, let me call it right away. This is called Taylor's theorem, okay? This is thanks to Taylor's theorem. Thanks to Taylor's theorem. So you had seen this before partially, because when you see this is x0 to over 0, so I'm gonna put just 1, okay? If you just take the first two terms, so these two terms, 1 plus x. What do you think is, what is the relation of 1 plus x to exponential? What do you think it is? And this is coming from calculus 1. What do you think is happening? I'm approximating my exponential around 0 with 1 plus x. Have you ever seen this before? Have you ever approximated a function by a line? Or the graph of the function at a certain point by a line? Yes, how do you call that? Guys, we're too worried about elections. Okay, exponential is like this, right? Exponential is like this. 1 plus x is what? 0 is 1. At 0 is 1, and minus 1 is 0. So this is the line. This is y equals 1 plus x. Somebody has to tell me now, because you had so many clues now. So what is the blue? What is this blue?
Is that the tangent line?
That's the tangent line. Thank you. Who say that?
I did, sir.
Who? Rene. Yeah, thanks. You made my day. Good. Because otherwise I will have to email all the people from Calculus 1. Yes, that's the, but you see, this is fundamental. This is the linear approximation for the exponential function. Can we do better? Yes. And that's fundamental for engineers because the error is, you see, the error of the approximation is good, very close to zero. But if you go farther from zero, the error is huge. Look at here. You see how big is the error? So and that's why these people, that's what Russians on the 70s were far away from us, sending spaceships to the space. So how do we solve the problem? We found somebody called Brown, and this guy started developing the rockets to go to the moon. Okay. Before Brown, what we were doing in the United States, we're working on Zeppelins and these, how do you call these guys? These big balloons. I don't know how do you call it. But we were working on Zeppelins.
Hot air balloons.
Air balloons, thank you. And they were working on Zeppelins and these balloons. And we wanted to go to space like that. And that's what they brought Brown to the United States. I think he was German, if I'm not wrong. And then he introduced all this rocket theory. So for some reasons, we didn't want to use this kind of technology because it was kind of the beginning of, like, it will be an open door for more violence, and indeed it is, right? So, but you know, so you can use science for the good or science for the bad. But so we're using for the good. So let's see. So if you tell me, okay, I don't want a linear approximation, that's bad because this function is not linear. Can you give me a quadratic approximation? I tell you, sure, here. And then another female student, they complain more, right? So they said, no, I want a bigger than that. I don't like quadratic. I want at least cubic. You want a cubic approximation? Here you go. And so on. So whoever start complaining, you got a better and better approximation for the exponential function, I give you more. Okay, so let's graph this to see how it looks. Okay, let's see how it looks. Let me look at Desmos. Then do we're gonna do y equals exponential. So that's exponential, right? So I'm gonna make my linear approximation. I'm gonna do I think we said 1 plus x, right? It's 1 plus x, okay, linear. But then somebody said, I want better. Okay, you want better? Here you go. 1 plus x. No, sorry. 1 plus x plus x squared factorial. So divided by 2. So you see, this is my quadratic approximation. So you can see here, for these points, my quadratic exponential approximation is better than the blue one. But look at this distance from here to here. My quadratic is better from here to here, right? From and in general, it's going to be better. Here is far. When it's negative, it's not very good approximation, right? but it's better than the blue one. Well, for maybe for some points not. Well, for positive it's better. Okay, so somebody wants better, I give you better. So you want a better approximation. So you want plus s cubed divided by 3 factorial. What is 3 factorial?
6.
6. You see? This one, the purple. So let me go out. You see my purple? So let me take these two guys out. Because I think I convinced you already that this approximation is better, right? Look at that approximation. You see? It's better. So let's do another one. X to the 4 divided by 4 factorial. What is 4 factorial? So you can remember.
12.
Second?
24.
24, correct. So that looks, oh, okay, you see, when I do 24, you see, it's getting really good when it's positive. Look at that. Look at that. When it's positive, but when it's negative, it's too far over here. So I need to put plus 25, plus x to the 5 to get a better. X to the 5 divided by, what is 5 factorial?
120.
Yeah, so you see, look at my positive. You see that approximation when it's positive? It's almost perfect. When it's negative, it's not good. Okay? So, but you see, this is 50. So if I go closer, look at, between this number, between -2 and 2, I have almost a perfect match. You see? Look at this. Between -2 and 2, the match is almost perfect. Let's compare with my linear. I can go back. So if you go to your linear, you see, this is much better than a linear approximation. Your linear approximation is just for calculus 1. You cannot go to your job saying that all that you know is linear. However, linear is really good, I have to say. Statisticians linearize most of the things. Also, we do nonlinear world is very difficult. The real world is not linear. Albert Einstein used to say the real world is not linear. Okay, that's what is difficult. So that's what we're gonna do tomorrow. Tomorrow we're gonna talk really careful about this power series and on the root test. Well, maybe I can just define it now, so we don't lose this momentum. Yeah, let me define it properly. So I'm telling you, from my point of view, this is what you had waiting for 2 years. Well, since high school probably. And I applaud you because, you know, that's why a lot of people don't like mathematics, because it's very difficult to show people what you can do with just fractions, you know. People just know fractions. I mean, how much I can show you with fractions? So very difficult, but you somehow fall in love with this on mathematics, and then you learn to love it. Otherwise, you don't be studying engineering or mathematics or physics or chemistry, whatever you're studying here. Okay, so let me define what is a power series. So I'm gonna set definition. definition. Sum of the form sum n equals 0 to infinity. Let me use c sub n times x minus a to the n. So let me write it here, some terms here. C0 plus C1 x minus a to the 1 plus C2 x minus a squared plus C3 x minus a cubed, and so on. Well, sorry, 1, 2, 3. This series, as of this form, is called a power series. In x minus a, or a power series center, or a power series center at a. Or a power series about a. Okay, so let me for the